Guys, I am back with yet another video, and today we are going to be evaluating the integral from 0 to infinity of 1 choose x plus 1 half with respect to x. And so, as you can see, we're going to be integrating a combinatorial expression here, which seems kind of wild until we simplify this down further and it starts to reveal its true self. It'll get a lot easier. Well, yeah, this is actually another integral from dailyintegral.com. This was the hard integral from July 2nd, I believe. And without any further ado, let's get straight to it. First thing I want to do is set this equal to I, as per usual. And I want to simplify the combinatorial expression down because we know that n choose k is the same as saying n factorial over n minus k factorial times k factorial. So that leaves us with the integral from 0 to infinity of 1 factorial over 1 minus x plus 1 half factorial times x plus 1 half factorial with respect to x. And we can simplify this a bit further to get 1 over 1 half minus x factorial times 1 half plus x factorial with respect to x. Now notice that this x here is a real variable since we're integrating across the positive half of the real line. So we can actually rewrite this in terms of the gamma function because we know that if we were to compute the factorial of a real variable, we wouldn't really be able to do anything without the gamma function because the gamma function is what allows us to take the factorial of, say, rational or irrational numbers. So we know that gamma of x plus 1 is the same as saying x factorial. That leaves us with the integral from 0 to infinity of 1 over gamma of 1 half minus x plus 1 times gamma of 1 half plus x plus 1 with respect to x. But we still need to simplify this a bit further before we can do anything with it. So notice how we're adding 1 to each expression within the gamma. We can make use of the gamma function's recursive property, which tells us that gamma of x plus 1 is equal to x times gamma of x to simplify this expression down. And so we get the integral from 0 to infinity of 1 over 1 half minus x times gamma of 1 half minus x and 1 half plus x times gamma of 1 half plus x with respect to x. And now these two terms allow us to rewrite the expression into something a lot simpler because multiplying these two terms out actually yields a specific form of the gamma reflection property, which is gamma of 1 half minus x times gamma of 1 half plus x is equal to pi over cosine of pi times x. And so we can substitute that into our integral as follows. We have the integral from 0 to infinity of 1 over 1 half minus x times 1 half plus x times pi over cosine of pi times x. And again, doing some more manipulation, we can take out that 1 over pi term. We get 1 over pi times the integral from 0 to infinity of cosine of pi times x over 1 half minus x times 1 half plus x with respect to x. And we can use the difference of squares property to simplify this expression below, because we know that if this is our a and this is our b, this simplifies to a squared minus b squared. So we are simply left with 1 over pi times the integral from 0 to infinity of cosine of pi times x over 1/4 minus x squared with respect to x. And we can take out that 1/4 factor, or actually it's a 4 because we have 1 over 1/4, so we have 4 over pi times the integral from 0 to infinity of cosine of pi times x over 1 minus 4x squared with respect to x. And now I'd like to make use of this even functions integration property and say that 4 over pi times 1/2 times 2, and this is correct because this is technically multiplying by 1, 2 times 0 to infinity of our integral. Since our function is even, meaning that if we plug in any negative value, we get the same value that we would as if we were plugging in a positive x value. Since our function is even, 2 times the integral from 0 to infinity is the same as saying the integral from negative infinity to positive infinity along the whole real line. And we can cancel this 2 and this 4 out to get 2 over pi. And that gives us 2 over pi times the integral from 0 to, across the whole real line of that same expression. And of course, you might be wondering why we made this a little less simple. It's because we're going to be taking this into the complex plane in just a second for contour integration, and the negative infinity to infinity is very helpful because on the complex plane, when we draw out the contour, we're going to be drawing it along negative r to r, so the whole real line. And so one last thing before we go complex is notice that this is cosine of pi times x that we have here, which is the same as saying the real part of e to the I pi times x. So we have the real part along the integral along the whole real line, e to the I pi times x over 1 minus 4x squared with respect to x. And so before we draw our contour, let's find what the zeros of our denominator are. We get -1 on both sides, the negatives cancel out. We have x squared equals 1/4. Taking the square root, we get x equals plus or minus 1/2. So here, it looks like we only have poles along the real axis. So these are technically only half poles. What we're going to be computing is half residues. And you'll notice that when we do Cauchy's residue theorem, that instead of using 2 pi I times the sum of the residues, we're going to be doing I pi, since these are technically only half residues. But yeah, without any further ado, let's go straight to the complex realm. It looks like our integral is going to be contour integral along the contour C of e to the I pi times z over 1 minus 4z squared dz. And let's just draw out our axes. We have the imaginary axis. This is our real axis. And we are going from negative r to r on the real axis. In other words, across the whole real line. Oops, sorry about that. So we are going across the whole real line and then curling back up into the complex plane and back down to negative r. And this is our big curve gamma, which goes counterclockwise. And so our poles lie here at -1/2 and 1/2, or I guess are half poles. And this whole contour is going to be called C. And so our contour integral along C of f of z dz is simply equal to the integral along gamma plus the integral along the whole real line, which would be from negative r to r. Perfect. So we know that by Jordan's lemma, the gamma integral converges to 0 because we have a function of the form e to the IAZ. So any contour integral of that form will always converge to 0 by Jordan's lemma. So we have a nice simplistic case whereby the contour integral is simply equal to the integral across the whole real line. The integral from negative r to r. Perfect. And so now let's compute those residues for the integral along the contour of f of z dz, which, like I said earlier, it's going to be a little different because we only have half poles. So we're only going to be multiplying by I times pi, but we're still computing the sum of the residues of the function f of z at its half poles. So that means we're left with I times pi times the limit as z approaches 1/2, which is one of our residues, times z minus 1/2 times e to the I pi times z, and our bottom expression, 1 minus 4z squared, when we take out a 4, we get 1/4 minus z squared, which then simplifies into 1/2 minus z, 1/2 plus z. Perfect. And so now we have 4 times 1/2 minus z times 1/2 plus z. And remember, we have two half poles, so we're going to be computing another residue. Limit as z approaches negative 1/2 of z plus 1/2 times e to the I pi times z over 4 times 1/2 minus z times 1/2 plus z. All right. So now just computing these out, we see here that if we factor out a -1 from this expression, we get negative 1/2 and plus z, which is the same as saying z minus 1/2. So these two cancel out and we're left with a -1 here in the expression. And when we plug in 1/2 into the whole expression, we get 1/2 plus 1/2 here, which leaves us with 1. So we're left with -4 in the denominator. And if we plug in 1/2 here, we get e to the I pi over 2, which is the same as I, since sine of pi over 2 is 1, and we're multiplying sine by I, which leaves us with I, just I. So we have negative I over 4 as our first residue. Here we can just cancel out these 1/2 plus z terms. Here we have 1/2 minus negative 1/2, which is the same as saying 1/2 plus 1/2. And that leaves us with 1 once again. So we have 4 here in the denominator, and when we plug in negative 1/2 for e to the I pi times z, we get e to the negative I pi over 2, which is the same as negative I, because if we plug in negative pi over 2 into the sine function, we get -1, and then times I, that's just negative I. And so our expression simply becomes I times pi times negative I over 4 times negative I over 4, which gives us negative 2I over 4, which is negative I over 2. So we have I times pi times negative I over 2. These i's multiply out, and we get -1, which cancels out this negative. So we're simply left with pi over 2. And that is equal to our integral along the real line, which would be the integral from negative r to r of e to the I pi times x over 1 minus 4x squared with respect to x is equal to pi over 2. But we need to let r approach infinity so that we get the bounds that align with our original integral. So we have negative infinity to positive infinity of e to the I pi times x over 1 minus 4x squared with respect to x is equal to pi over 2. But we need the cosine of pi times x term from this e to the I pi x. So I'm just going to expand it out. So we have the integral from along the whole real line of cosine of pi times x plus I times sine of pi times x over 1 minus 4x squared with respect to x is equal to pi over 2. And so notice that we can fracture this fraction to get cosine of pi over x over 1 minus 4x squared plus I sine of pi over x over 1 minus 4x squared. And we split the bounds to each integral. So if we're talking about the integral along the real line of I times sine of pi over x over 1 minus 4x squared, that's actually 0, because sine isn't an even function, it's an odd function. So, and we know that the integral along the whole real line of any odd function is simply equal to 0. So that leaves us with just the integral along the whole real line of cosine of pi times x over 1 minus 4x squared with respect to x, which is equal to pi over 2. And now, if we go back earlier to the expression we got just before we switched to the complex realm, we have 2 over pi times cosine of pi times x over 1 minus 4x squared. But we know that this is now equal to pi over 2. And so these pi's cancel out, these 2's cancel out, and our final answer is simply the integral along 0 to infinity of 1 choose x plus 1 half with respect to x. This is simply equal to 1. And honestly, that was quite the journey to get an answer as simple as 1. This whole journey was just very impressive. We have the gamma function, we have the reflection property. We took it all the way to the complex realm, and thankfully our situation was quite simple there. We made quick work of that residue, and we got that the integral along the whole real line is equal to pi over 2, which allowed us to say that this is equal to 1. Honestly, quite an impressive and elegant journey. Thank you guys so much for watching as usual. Tune back in for some future videos, and I will see you all later. Goodbye.